Hi, I'd like to talk with you about how to use Hilbert curves for computation. They're used for a number of things. Most often, a simple form of clustering. It's not as strong as other clustering methods, but you can quickly cluster data with Hilbert curves. Hilbert curves are also used for databases where they help index multidimensional data for easy storage and retrieval. There are also applications in visualization and for optimization. It's possible to apply a one-dimensional global optimization across 2 or 3 or 4-dimensional data by first unraveling that data using a Hilbert curve. I just said we unravel data with a Hilbert curve. Let me show you what that looks like. This is a Hilbert curve as you might see it on Wikipedia or as it's used for visualization. It's a pretty picture. This is the level 1, level 2, and level 3 Hilbert curve. It goes up to an infinite number of levels, and really these are pseudo-Hilbert curves. As you get to the infinite Hilbert curve, it becomes a space-filling curve. I don't think of the Hilbert curve this way, as this line. I think of it as a sequence of integers. So on the left is the Hilbert curve for level 1, meaning you have 1 bit of information. On the right is the Hilbert curve for level 2, meaning there are 2 bits of information. So that means you can store anything from 0 to 2, 2 to the 2, or from 0 to 4 on the right-hand side. And what it does is take an x and a y index, so I could be at x equals 1, y equals 2, and it turns it into a single Hilbert index, 7. So there are no repeats of the indices inside of the square. This is a nice way to turn a 2-dimensional indexing system into a 1-dimensional indexing system, or vice versa, 1-dimensional into 2-dimensional. Some of the restrictions are that it is usually, for most algorithms, done on a square, and as well, it's usually powers of 2. This is the way that we do the conversion. So bijective Hilbert is a Julia library that does Hilbert conversions. It's an algorithm. On the left, we have the x and y indices, and on the right, you have the single Hilbert index. In this case, it's for the level 3 Hilbert index, meaning 2 to the third is 8. So this goes from 0 to 7 on each of the axes. And the Hilbert index needs to be able to store 6 bits of information, which is what you see on the right. So as you see below, you encode from an I and a j index into the Hilbert index, or you decode from the Hilbert index back into the I and j. We call it bijective because there's one for each point in the x and y, there's a single point in the Hilbert space. This is always true as long as you know the size of the space of the Hilbert curve. As well, this works in 3 dimensions. Here, you can tell that this is a single curve in 3D space. If you look, it starts at the blue and it ends at the red as it spins here. But I wanted to make the point that this is in higher dimensions. It's in 3, 4, 5 dimensions. And that is actually one of the times that it really becomes useful, is to unravel a higher dimensional object into a single dimensional object. But the place I most often use Hilbert curves, and the example I'm going to show you today, is for saving geospatial data. So shown here, the blue lines are indicating how I would store geospatial data that's in a matrix. So Julia is column first, which means that the row moves faster than the column in terms of the axes. And so if you were to take a matrix that represents an area of land, say, the strong blue line indicates that everything in the column is stored next to each other when we store it in memory, because memory is linear. And then there's a jump, and then it goes to the next column. Now, as a consequence of this, if I want to ask, give me all the data that's near a particular point in space on the land, I would have to do a query like this orange rectangle. It's a rectangular query region, and I would find that I would need to retrieve several different pieces of memory. If there are more pieces of memory to retrieve, there are more separate retrievals and it's less efficient. And so we usually optimize that by trying to ensure that when we retrieve data around the query of interest, that data is near each other in some way. One of the ways that we do this is to block the data. Here's what blocked data storage looks like. Again, there are rows and columns. Again, this is oriented towards the columnar storage. But when I have my orange query region, you can see that the data within the orange query region tends to be more close to each other than it was before. So this only overlaps 4 different regions of space as opposed to overlapping 8 or something that we had last time. Well, the Hilbert curve, if we go back to our original image and look on the right, the Hilbert curve will tend to ensure that data that is near each other in 2 dimensions or higher dimensions is also near each other when it's stored in the order of the Hilbert curve. And that means that data will have more spatial locality for storage and retrieval. And by spatial locality, I mean in the space of memory or disk storage of a computer. The way to calculate this is not too difficult. Using the bijective Hilbert library, you could take your J and I indices, right, your X and your Y, and sort them. So if you had something from 0 to 16 and 0 to 16, you could sort it using the Hilbert index associated with each of those X and Y values, and that would reorder it in the same order as the pretty curve from blue to yellow that we saw earlier. And below is an example for higher dimensions. In this case, it's a 3-dimensional example using a different algorithm, but still a Hilbert algorithm. And here's an example of how I used it for some of my research. So this began as a land scan map of Africa. So it was the population in each pixel. First, I arranged it into blocks of data because the blocks of data are an efficient mechanism. And then I sorted those blocks according to the Hilbert index. I excluded all blocks for which there was no population. That's why you see white over the water. And then I took the sorted indices and took groups of 20 of them at a time. Now what I'm going to do with these is send each one to a separate computer to work on. So this is for distributed computing. What you're seeing here is a way to cluster data such that each of the machines in the distributed computational cluster has a relatively compact 2-dimensional space to work with. You could cluster it, but there's several advantages here. One is this is agnostic to the size of how much data you send to each of the machines. I could split it up into pieces of 20. I could also split it up into pieces of 3. And as well, you not only end up with clustering, but I also have a very easy way to walk through those clusters. I have indices into the clusters themselves. Thank you.